So basically I'm going to talk about anomalous transport. So of course I will give you definition and motivation. Basic motivation is biology. I'm a theoretical physicist, but nowadays in order to get grant money for research, you need to say that, oh, that's very useful for health, this is very useful for United Kingdom people, and that's why we turn from physics to biology. So, and of course it's not just general biology, but also which happens in our body. So today I'm going to illustrate very beautiful mathematics by using a lot of biological examples. And of course from probably human behaviors, many examples. So basically I'm going to illustrate this new really interesting research involving so-called fractional differential equations in terms of biology. Okay, that's something written here. And this is my team. We work, of course, together. It's part of team. This is my postdoc and new PhD students from Denmark. Peter, former postdoc, he just left before Australia. My PhD student Steve, and that's me. So it's a very small, anomalous Manchester team. Right. Okay, so first, of course, let me give a brief outline what I'm going to talk today. First, I will just introduce to anomalous transport. So many examples again involving biological application, it's so-called subdiffusion and superdiffusion. And then I will give you some particular results involving subdiffusion of morphogenes, metapopulation, transport on network, and probably superdiffusive transport involving label. Of course, I will give you all definition, of course, all illustration. So please don't worry. Okay, let me start with an example. I'm sure you're familiar with diffusion. So diffusion is a basic process, and if we have a Brownian particle which moves around, randomly as a drunk person, then, this several trajectory. And it's very well-known result that B, it's a Brownian motion. If we square this, take mean value, this is proportional to time. And what is between time and this mean square displacement, we call it diffusion coefficient. This is pretty standard. And if we have a lot of particles behaving like this, then we could introduce a standard diffusion equation. This is diffusion equation, and it's clear that the rate at which density of particle change with time depends on this Laplacian. 3D is Laplacian, otherwise you just second to it. And this is the same diffusion coefficient. So I'm sure everybody knows that simple concept of diffusion. It happens everywhere. But now, people found that in many cases, it's not diffusion, but subdiffusion. So mean square displacement. Look, this is x, it's the particle position, it's a random trajectory, and if we square it and take mean value, then it's proportional not to time, but you see time to the power mu. Mu is very important parameter, so please pay attention. Mu is so-called anomalous exponent, and mu varies from 0 to 1. So here for Brownian motion we have linear dependence, here we have sublinear dependence. So at first glance, well, it's not big difference. Okay, this is linear dependence, this is sublinear. The question is, what kind of equation we have for the particle behaving like this on macroscopic level? If we have a lot of particles, that's a crucial question. And of course, the equation will be not like this. It will be a very complicated equation. Now, okay, and that's an equation involving Riemann-Liouville fractional operator. Now, that's part of this equation. Since I work together with biologists, and recently they asked me to explain the subdiffusion, because subdiffusion happens all the time on microscopic level when we have a transport inside cell. Biologists found this law from experimental point of view. And then they asked me to explain them what is the reason why we have subdiffusion, what is the physical reason behind this behavior. And of course they explained the mathematics. And now, can you imagine if you show biologists, I respect biology, believe me, but if you show them that the equation describing subdiffusion looks like this, and that involves Riemann-Liouville fractional derivative, which is defined through the integral, and this is convolution. Can you imagine what might happen? That's what happened actually. They invited me to give a talk, and after, when I showed that equation, of course they stopped talking to me, because you're a mathematician, crazy, you need a proper language to explain biologists what we are doing, theoretical physicists. So sometimes it's not easy. And you will see that subdiffusion is extremely important for many processes taking place in our cells, in our brain. I will give you examples. So it's biologically, it's very important. But the mathematics behind this is very complicated. Have you heard about the Riemann-Liouville fractional derivative? I'm just curious. So basically, I'm sure you're familiar with the first derivative, second derivative. But between first and second, of course, we have so-called fractional derivative. It's like I always ask students, what is 3 factorial? And then, of course, everybody knows. My students know that. But if I ask them, oh, what is 3.2 factorial? They start immediately. So I'm sure you've got the same experience working with students, because they just memorize some definition without thinking what is behind. So the same things for actually fractional derivatives. So first derivative, it's clear, second derivative, it's clear, but this is like fractional derivative, because remember mu is something, the exponent varying from 0 to 1. And that's a fractional derivative, that expression. Okay, I'll explain this later on. So now I just want to pay attention. We need sometimes to find a common language with, let's say, common people. So now I'm going to explain the reason why this object occurs as a result of physics. Right, this is just an example. Well, this is the surface of the cell, for example, and it's overcrowded. It's not easy to move around. It's not like a Brownian particle moving freely in space, because there is so many obstacles. It's a very complicated object, and that object, for example, moves very slowly. Or transporting signaling molecules in neuron. So this is the standard picture for neuron. And neuron with spiny dendrite, this is, you see, blue spiny mushrooms on dendrite, also induce subdiffusion. So if we have a, say, x squared, that's x, is the position of particle moving in space. And if we take average value, then it's proportional to time for Brownian motion. And again, if we take subdiffusion, it's t to the power mu. So mu less than 1. So it's like slowing down of the process. So particle moves slowly. Why is that? Well, as long as biologists see slowing down their conventional way of thinking, okay, we have diffusion coefficient here. It's like, say, 10 minus 3. And if we have slowing down, what we have to do? We have to change that coefficient, like make it 10 minus 5. And it doesn't solve that problem, you see? Because for subdiffusion, we have 2 parameters, so-called fractional diffusion coefficient, and some parameter mu. So So that's just decreasing diffusion coefficient doesn't give you the answer. Now, what is the reason why we have subdiffusion? Why we have slowing it down? Okay, I will give you an example. Okay, this is neuron, and this is part of neuron, and so you see, like a physicist, you can see the tube, and on the tube you have something like mushrooms, and we call it spines. I'm not going to explain biological what they do, but okay. Right finger. So dendrite. So those things in our brain. This subdiffusion happens in our brain 24 hours a day. It's very important. So dendrite can be represented by the tube, and on the tube you will have something like mushrooms. And the particle, like iron, it moves along the tube, and sometimes, occasionally, it hits that space, and then it just traps inside the spine. So it's trapped, and that's why it induced delay. But it's trapped in a very different ways, like subdiffusion, because in order to measure trapping time, let's say this is random time, the particles spin inside this dendrite. Oh, sorry, spine. This random time has a distribution. And if this distribution behaves like 1 over t to the power 1 minus mu, that's what's written here. This is time, this is distribution of time for particle spending inside this tube. We call it residence time. It's a power. And if mu less than 1, if you calculate the mean time the particles spend inside the dendrite, for this distribution, for the case mu less than 1, first moment is just diversion. So this tends to infinity. And that's the main reason for subdiffusion. Because I'm not sure that everybody is familiar with diffusion, because if you are a statistical physicist, it's very easy to find statistical model and find out expression for diffusion coefficient. Diffusion coefficient is usually x squared, which is mean square or jumps, over mean value of time. This is usually finite in many cases. But if that tends to infinity, diffusion tends to 0, and the whole theory of Brownian motion just breaks down. That's an idea. And this pretty universal phenomenon, I will give you another example, because this is dendrite, but it can be anything, just imagine this is like a street, shopping street, and this is just shops. I'm familiar with this shop like Gap, Louis Vuitton, and McDonald's, just shops. And just imagine the customer, it moves along the street. It moves randomly, sometimes just shopping, and then occasionally you get in this shop and spend some time. Under normal circumstances, how many time you spend in the shop? Like 20 minutes? 5 minutes? Well, of course, it's random. So you need the distribution of time you spend in your shop. And under normal condition, of course, you will have diffusion. But now just imagine we have sale. Stale means it's a lot of offers, you just get in and you just trapped inside shop because a lot of things, you need to change them, changing room, and of course sometimes, well, it depends on people, but sometimes it's just trapped, and that's just an illustration of subdiffusion. So it's slowing down the whole process dramatically. And so this is just an examples. So have you got any questions regarding the subdiffusion?
So in the example for the shops,
yes.
So the people turn again to the streets, right? So by diffusion is something like I was thinking the particles are forget in some sense that they don't return. I was thinking
well,
the process, but there is some moments in the people return again on the flow of the people, right?
No, they move randomly, you know, back and forward. That's induce some kind of dispersion. But when there is just trapped at some place, dispersion becomes slowing down in a way. So, you see, the question is, what is the reason for this law, the power law? It's a typical example of so-called non-Markovian process. If we think of rate of escape, I will give you an example. I'm sorry, we have to work together all the time. If I introduce escape rate, just imagine the person inside shop or iron inside this very complicated spine inside our brain. Of course, there is always escape rate. But for a non-Markovian process, escape rate is not a constant. If it's constant, it's a standard theory of Markovian process, and usually mean time, of course, is proportional to escape rate, gamma. That's a standard theory, any kinetic theory. But in this particular case, escape rate depends on residence time. And if we assume that residence time, tau, that's in. So let me explain. The rate of escape from some position inversely proportional to residence time. So in another word, the more time you spend inside something, less likely you escape. That's an idea. If you start to talk to biologists and say, look, we introduce probability density function for the residence time, and then we introduce power law in a such way that first moment is divergent, biologists stop to listen to you. For obvious reason, because for biologists it's difficult to imagine mean time is infinite. They say, oh, this is mathematician, you know, with all these tricks, you know. Don't. They, of course, they are very polite. They say, oh, interesting. We're not going to work with him, definitely. Now, but if you explain them, the idea is that subdiffusion occurs as a result of this law, they could listen. Because this is like common sense. Anyway, like in biology, cell. Sometimes when you describe cell movement, you can write down transport equation involving diffusion equation. But why cell moves randomly, right Brownian motion? If cell finds a good place to stay, lot of oxygen, food, why to move? It just stay. And the longer it stays sometimes, it's less likely it escape. Because it's good environment, and well, it's the same like human. Okay, I'll give you an example, like in academic life. If you are PhD student or postdoc, you move around all the time, especially in Europe or United States. But as long as you get a permanent position, you're trapped. You're trapped for this reason. Of course, if you are a professor, why to move? Because you're trapped for a different reason. Because you've been promoted, you've got a mortgage now, you've got a family, school, all social environment around you. You are trapped, you don't move at all. So this behavior. The longer you stay in some particular position, less likely you escape. And this is universal law. That's why with my PhD students we apply for different things. It's about state of mind, for example. Of course, our political preferences. We are move right and left sometimes, like random party. And of course, because of it's a lot of influence from newspapers, news, we move randomly like thermal noise. But also we have own agenda, and let's say we are politically oriented on the right, we move on the right. And the law is psychological law. The longer you stay in a particular state of mind, less likely you escape. You're just trapped in your state of mind. So you just say, oh, I'm 20 years voting for this party, don't touch me. Nothing changed my mind. So what I'm trying to say, this is really universal law. And because it's so universal, and you can't stop me, I'll give you many, many examples, of course, of this law. That law actually introduced this power law distribution of residence time. Again, residence time is also, it's not just about particular residence time or time spending in particular space. Again, it's a state of mind, it's many other things. But then, this law generates, oh my God, yes, this fractional operator. So, of course, I skip all details. So, my message today, of course, if you're interested, you will learn. But fractional derivatives like that, closely related to power law distribution for residence time, such that mu less than 1. And this mu is just the same everywhere. Here, mu is just the same. And also it relates to this law, and now mu is here. That anomalous experiment. So, right?
From your last comments about this complex socio-psychological behavior, and,
yes,
I think that's another big I mean, returning to this problems of systems of particles, and
well, I'll give you an example. We recently published a paper in physical. Like 2 years ago, I thought this is just a joke about professors. That's what I thought. But then we started to think, and then we translated this joke into Physical Review Letters paper. And this is really good journal. It's physics. Okay, go ahead.
Well, returning to the more simple system of
yes.
And also in relation to this equation number 1. So is there any correspondence between this fractional derivative expression and the generalized diffusion equation, like Smolkowski or Fokker-Planck equation?
Well, that's a good question. Of course, you see, if we have random process, and if it's like diffusion-like process with first and second moment finite, then of course it generates like any master equation for that random process can be reduced to Fokker-Planck equation. And of course, Fokker-Planck equation has two components. This is standard Fokker-Planck equation. It involves drift, of course, because of the force, external force, and diffusion coefficient. Now, the same way, if you introduce so-called non-Markovian random process, it can generate so-called fractional Fokker-Planck equation. That's a particular example of fractional Fokker-Planck equation. That's a connection. So there is no shift in this operator. Of course, it's very easy to introduce that shift as long as you have external, because this is due to a noise. If you have external force, you will get an operator involving first field. Standard. So it's like hierarchy. If you have a standard process, most of the time, because of central limit theorem, you will get Fokker-Planck equation. But in this particular case, when the first moment is divergent, you see, that central limit theorem breaks down, and you cannot derive classical focal length equation. That's an answer.
So in the cases of when it is possible, I imagine that there exists a way to obtain this coefficient move in terms of interparticle interactions.
Right. Of course, focal length equation gives you a picture when particles don't interact. This is a linear approximation. Interaction is a different story.
No, yes, they interact. In the Smolkowski equation.
No, wait. I'm talking about classical focal length
Yes.
equation. Of course, if you introduce interaction, for example, yes, you will get some terms proportional to the product of two functions. Yes, and you can do it. And that's what I'm going to discuss today. Exactly, because this is an example of linear equation. And because it's linear equation, and this looks complicated, but in fact, this is just convolution. And since it's convolution, if you apply a Laplace transform, it becomes so easy algebraic equation. And all this fractional business, most of the time, based on linear equation. You just problem. And then the question was, quite recently, people started to think how to extend this linear equation for a nonlinear case when particles interact. Because in biology, all the time interact. Smolkowski, it's about so-called diffusion limited reactions. You need two particles meet each other. And of course, it takes time, and then, of course, interaction. So how to introduce interaction? And that was not easy question, and that's solved quite recently. That's what I'm going to discuss today, actually. So basically, I introduced fractional equations so far. But I'll give you an example from, again, social life. How to introduce that behavior? If we have, not social life, let's say cancer cells. If you have a lot of cancer cells in one space, then, of course, because they consume, there's no food, there's no oxygen, and they started to move away from that place. It's quite dangerous, actually. That's the reason why it's difficult to treat cancer cells, because they are mobile. Why they move? Of course, because there's plenty of other particles here in that place. So you need to introduce interaction between particles in such way that induce movement of the particle. This is just an example. And of course, sometimes this is a very famous phenomenon in biology. If we have a lot of bacteria moving around, and if they found a place which is really good, they interact in a such way they don't move. So, it's plenty examples in biology. And if they move subdiffusively like this, the question is how to extend that equation to nonlinear case involving particle interaction. So it helps me a lot with this question, because that's what I'm going to discuss today.
But also this description, I think, is more adaptable to non-equilibrium situations, because Smolkowski and Fokker equations are equilibrium equations where there is a very well-defined temperature and things like that.
Yes. Well, that's another question about what is induced random movement. Either it's thermal noise or it's just non-equilibrium situation. In biology, most of the time it's not equilibrium situation, yes. But again, it's a matter of discussion. But we'll talk about later.
So,
Also,
it's
subdiffusion
or superdiffusive behavior. It also depends on the time scale in which you measure the phenomenon, right? Because on the long time scale, this problem of the
that's
it behaves normally.
Oh yes, of course. If you started to talk that this, basically the idea is that there is no this is like microscopic scale, and when we're talking about subdiffusion from physical terminology, it's so-called scale-free behavior. There is no microscopic scale. And as long as no macroscopic scale, all scale are important. And the question is what we have in macroscopic limit. Of course, in physics, in biology, everything is finite. So the biologists observe subdiffusive behavior at some certain window, time window. And of course, if you just continue, then it leads to standard diffusion. But because time window might be very long, and of course it's important because all this living process happens during this time. So that's why it's important. But of course, it's the whole limit, everything becomes diffusive. So you need to introduce so-called cutting procedure. That's also it's done, of course. This is superdiffusion. Now, this is example what happened in so-called intracellular transport. You see, like if you have cell, I'm sure you're familiar with that. Cell is not just space inside which we have so-called, microtubules. And the particle actually inside cells moves along microtubules due to so special transport involving not proteins. And the main idea is if particle moves in this direction with certain velocity, and then if it changes direction according to some random Poisson process, then it's also induced diffusion at the end. But if I keep this direction, and then the longer I stay in this direction, less likely I change the direction, that's introduced so-called superdiffusion. So, like, that's observation for cancer cell. When cancer cell moves away from the core, where there is no oxygen, and you see it moves, and it's getting better and better. More oxygen, why change direction? Just keep direction, you just keep. But it's not ballistic. Because sometimes you say, okay, stop, or change direction. So it's still, because superdiffusion, it's something between diffusion and ballistic movement. Well, that's just another example. This is just for common knowledge. Because nowadays it's very popular to talk about Levy wall, Levy flight in physics. And sometimes particles jump in space, of course. It's not just about waiting, but they jump. Animals, of course, sometimes jump long distance. And if the second moment of jump is divergent, so again we have a breakdown of central limit theory, then instead of Laplacian, we will have a so-called fractional operator. Again, I'm not going to give you details, but that's just an idea. So you see, as long as you have microscopic behavior, and then if mean waiting time divergent or mean squared for jump is divergent, then you might expect a very unusual behavior in terms of mathematics. So that's rational. But I'm not going to discuss this today. Just mention. Okay, now. I'm familiar with so-called reaction diffusion equations. This is basically main tool in mathematical biology. So as long as if you want to study an application of mathematics in biology, you open any book, undergraduate book on mathematical biology, and it's always so-called reaction diffusion equation. The idea is almost trivial. If you have that equation, so let's say this is density of particles, and then we have a transfer, let's say diffusion in space. And then if you want to take into account the proliferation or the death process, it's very easy in mathematical biology. You say, okay, let's put on the right hand side of the equation production term. It may be any function of the density. Of course, we call it diffusion reaction equation, and it's a non-linear equation, and of course, it's a lot of literature on that subject. And it doesn't matter, one equation or two equations, but the whole idea is you always separate transfer and reaction. So you see, it's easy to work with, especially with PhD students. You are a supervisor, like a professor, and if you want to take into account something, different, you just say, oh, let us write down on the right-hand side something else, and study this. Traveling waves, Turing instability, many other problems. But the question is, why, from physical point, why you just said this is transfer, this is reaction? Why they are always separate? Or you can introduce, for example, transfer process. You can say, okay, if we have not just diffusion but also advection in space, we have just wind. If we have wind, we move in one direction, right? So I just put this is wind, and then I put gradient of rho. So it's always they separate. The question is why? Well, my answer is now that if instead of Laplacian you got a fractional operator, this theory doesn't work anymore. So you cannot separate transfer with reaction. I will show you why it happened. But you see, that's what happened nowadays in applied mathematics. If biologists ask applied mathematicians, look, we have subdiffusion. Okay, easy. You just put like here, Kaput derivative, for example, and that you have a fractional operator. Now, but apart from subdiffusion, we have also proliferation of particles, which always happened in biology. And applied mathematician can do the following: just okay, let us add this nonlinearity, which describes proliferation, production, growth. This is really wrong idea. So, and you see, in mathematical literature, especially in mathematical biology literature, it happened all the time. They just write down the equation and started to find the traveling wave solution to prove uniqueness. This model is completely wrong. You see, this is again, it's my second message. As long as you have a subdiffusive process, then that procedure of separation of transfer and reaction doesn't work anymore. And that's a very important message. Now the question is what to do.
It's a kind of branching, it's a kind of branching process. Branching process.
I'm not sure I understand the question.
The behavior of this process are similar to branching process because they are I think because it's the
okay, let me illustrate an example of this idea, because this is just general idea, and now I illustrate it. Then this is a classical problem in morphogen theory. It's like random morphogen molecules. They are produced at some boundary. Let's say this is X, this is space, this is 0, and on this boundary we have a production of new particles. We call it morphogen molecules, and they started to move randomly according to this diffusion operator. They move just Brownian particles. But when they move in this direction, they also die because of different reasons. So that equation is written in any biophysics book, because morphogen gradient formation is very important for our life. This is a very classical example in biology. So you see the rate at which the density of this morphogen molecule change due to transfer, diffusion, and the death process. So you have minus, and theta is the rate of death. Sometimes it depends on the density, sometimes constant. So, and if you have a production here, of course, sooner or later, this equation has a stationary solution. And And then you will find this profile, and that's a classical problem. But there's a lot of experiments nowadays that all these morphogen molecules, they move not like diffusion, they move subdiffusively because of different reasons: obstacle, trapping, reactions, many reasons. This is the experimental fact. Now the question is how to take into account subdiffusion, so instead of that operator with something else, and the death process. So you need to formulate random model from the first principle. The particle moves randomly. Then you do all this procedure. You first derive mass equation, then you will derive microscopic equation. And if you do this properly for subdiffusion, you will get the following equation. It's a very complicated equation. Let me explain briefly what is the main idea. So you see, the rate of change of the density now depends on two terms. This very complicated term I will explain in a minute. And of course the death rate. So you see minus. But look, this is function describe the rate at which death happens. And now, look here, we have diffusion, second derivative. It's like in four-point equation. But inside second derivative, you've got many terms, including fractional derivative. And look, here we have death rate as well. So when you derive microscopic equation, death rate appears here as in the previous case. See? Death rate. But instead of Laplacian or second derivative, you will get this ugly operator. Very ugly. But that's what happened. So it's pretty recent result. For linear case, it's derived by my colleague from Spain and the United States. But in non-linear case, we did it with my PhD students. So when we derive that equation, the question is, what can we do with this equation? And because this is really a very complicated operator, because it's non-linear, it involves fractional derivative, it's just nightmare. But in the limit, what we found, in the limit, we have a very nice equation in stationary case. So, but the price to pay for this simple linear equation, that diffusion coefficients now depends on the rate at which particle die. Okay, it looks like mathematics, a new equation. If you ask biologists how they get diffusion coefficient, do you know? I mean, they've got some process, and sometimes they use diffusion coefficient. Do you know? It's not easy directly to measure diffusion coefficient. It's impossible. How they do? They just say, okay, 10 minus 3. Why? Because if we put this number 10 minus 3, we will get right answer for other experimental data. So this is just fitting parameter most of the time. And now we, at first time, found that it's not just a constant. Diffusion depends on the death rate. This is quite new result. I will try to explain. Of course, skip all mathematics. It's a lot of math here. But if I ask you, what is diffusion coefficient? What does it mean? Diffusion coefficient, the meaning is a measure of mobility. Now, if particle moves and sometimes trapped and don't move, how to increase mobility? How to make system mobile? So what do you think? If particle just trapped, they're getting cold and old. We just need to kill them, you know. Very simple. If particle don't move, just kill it. And that's what happened in the nature. So that coefficient, diffusion, becomes dependent on the killing rate. That's an idea. So if some particle trapped, then in order to increase mobility, we just need to kill those trapped particles. And that actually the idea of cutting off. You see, if particles just don't move, and if we kill them, it means basically we're back to the diffusion limit. So it's like cut off. If particle just living long time, then well, we need to cut that light. And that's diffusion coefficient. Also, why this result is my work. That's a typical journal department paper. The nation of statistics. So, message is you can't separate transport and reaction, and diffusion depends on killing rate. This is pretty unusual for physics because diffusion all the time is just intensity at which we have a Brownian particle pushed by thermal noise. So diffusion is always proportional to the temperature. That's a famous result in statistical physics. So now with this non-equilibrium system, very funny results. And good things about this fractional business is it's good to work with PhD students. As long as you do something, it's new. It's really good. Because to make progress, let's say in fluid mechanics, oh my God, it's almost impossible. Or in other areas, so many areas in which any tiny step. But when you work with PhD students, sometimes it's very important to excite PhD students because, oh, it's really great, you know, it's funny. It's not just incremental work. You produce something new. And then, of course, opportunity to give a talk in a conference. That's my message. We need to excite our PhD students sometimes to do interesting work. Right. That's I'm going to about to introduce that work. Yes.
How does it look like the Einstein relation for this fractional case between diffusion coefficient and mobility?
No, you can write the.
It's the same?
Yes, almost the same. Yes, it involves so-called. It's about dimensionality analysis because it's a fractional diffusion coefficient. It's not like meter squared or second. You need to introduce X factor, and of course, its relation again is some.
And the argument to derive this relation, the classical argument is the balance between diffusive flux and convective flux.
This is not linear case. This is not. It doesn't work. That's not the case. But in a classical fractional business, that's exactly the argument people use. Yes, just of course they just use the standard general idea from statistical business to find the relationship. Yes, of course. Now I will give you an example of transport of meta-population network because nowadays. Network is still a hot subject. People like networking analysis, and because network is everywhere. Again, in biology, in human behavior, just everywhere. And I'm sure you're familiar with this scale-free network, Barabashi style. You have some nodes, you have connection, and they introduce so-called K parameter. This is the number of connection the node has. And that famous law, power law for number of connection can be, of course, derived by using standard Barabashi arguments about preferential attachment. But now imagine that we have scale-free network and transfer inside that network. So particle spend some time in some node, and then move to another node, and move to another node, and we just generate transport inside network. the classical result in this theory for transfer is this one. So, well-connected nodes are more populous. That's the classical result in network theory. So if we have some particular point with a lot of connection, and if you organize random walk in this network, then if the node has a lot of connection, it attracts a lot of particles. That's a common sense result. It's very famous. But behind this result is so-called Poissonian behavior. If particle sitting inside node, and then it spends some time, of course, and usually it's like Poisson process, you just jump to another node. But human it's not just Poisson process. It's a Barabashi result. I'm familiar with the famous result of Barabashi, like how we send emails. It's not Poisson process. We just drop in our office, and then some urgent emails. We just send like 10 emails, and then what happened? Between activity, we have other things to do, to give lectures, to take care of other things, and then it's a long period. And sometimes we think, oh, you need to be very careful to respond to emails, and sometimes it's a very long time before we send another email. And this is a classical result that distribution is not a Poissonian. Now, we thought, let us apply non-Poisson behavior involving this waiting time. Not waiting time, escape rate. Mu over tau plus tau 0. So, with let's say, just imagine, hit the particle inside node, and then the longer the particles stay inside node, less likely it escape. We just like theoretical physics. Let's do this, okay? Let's find the result is just dramatically change this behavior. Actually, it's completely changing behavior. As long as we introduce this piece with some particle with this kind of behavior, with anomalous behavior, all these particles are attracted by these nodes. So this law will be completely destroyed. So, and we found in the sociology literature that famous axiom of cumulative inertia, that when individual escape probability from a node decreases with residence time spent in this node. That's a lot of evidence, data on that kind of behavior. And as long as we apply this law, we introduce, of course, power waiting time distribution, and that result published in this paper. It's quite recent, it's just a few months ago. And Helena staged as my second year PhD students. And of course, it's good for PhD students when you are just second year to publish in this journal. It's really good for your future career. It's really, I'm very happy. And again, if you have a standard behavior, like Poisson behavior, the flux, so the mean number of particles escaping particular node is lambda, which is, of course, typical parameter for Poisson process, and the number of particles inside this node. This is classical law which used all the time. Now, if we have that kind of behavior, instead of this law, it can be derived, and it involves now fractional operator. So we not just simply change something from another, it's derived. And that's the final result. Ultimately, all individuals in network are attracted to nodes with this kind of behavior. So it's quite new result, because in network theory, people believe that the more connection you have, better for you. That's famous result. And this dominant behavior. But apart from the number of connection, it's important parameter the time you spend in that node. Like, have you noticed when you drop in a shop, the managers design shop in such a way in a mall that it's not easy to escape from that shop. And there is statistical data. The longer you spend in a shop, you spend more money in that shop. So this is important to trap customers in a shop in different ways. That's why they put nice pictures, you know, it's a lot of tricks. And we are human, psychologically, we unconsciously behave that way. So this is not just out of blue theoretical results. It's everywhere. It's trapping. It's very important to trap people. That's what the political party do. You know, you need to be trapped. You know, it's a lot of things happening nowadays. So my point is, for network, it's important not just number of connection, but also the time you spend in a particular. If you just sometimes surfing network, you know, some sites are very attractive, you know, for different reasons, of course. But the main idea to attract you. And sometimes you open some, you know, site. I don't mention, it doesn't matter. And you're just spending hours with this site. Have you noticed that? So it might be not many connections, but as long as you are attracted to a particular site in the network, oh my God, dominant behavior. That's what now done mathematically. So again, it's about infinite time you spend in a particular site. That's right. Of course, you need some, well, let me tell you. Now, well, this is real life for our scientists. As long as you need to get a big grant, you need a good publications, of course. How to get a good publications nowadays? In physics, for example, you want to publish in physical journals. But if you do nice theory, most likely that your paper will be rejected nowadays. Why? Because they say, oh, where is experimental data? This is just pure theory. It's like, you know, mathematical exercise. This is just an excuse. So you need nice theory, good data for motivation, and then data confirming your theory. So this whole package, of course, numerical simulation, nice theory, and then if you cover all this area, then there is no excuse for a reviewer to get rid of you. You know, that's why I asked my PhD student to find some evidence of that kind of behavior. And we found because usually in standard theory, people consider the number of particles inside node as a function of time. Now we introduce so-called structural density. So because you see residence time is so important, and we say, now it's not just time, but also we introduce residence time, the time the particles spent in particular nodes since the last jump. So it's structural density. And then we found a very nice limit for this function. It doesn't look nice, but it's like U-shaped distribution. And then we found this data. So we analyzed the number of people living in Milwaukee. It's a United States, very nice area. It's a data. And we found the data which measuring the time the humans spend in particular nice area since the last move. And we found this distribution. So the place is attractive, according to the theory, is that most people, they moved, let's say, 20 years ago and still there, like university professor. As long as you get a position, 20 years ago, most likely you will be the same person. So people, in terms of employment time or residence time distributed like this. Either you're just newcomers spending 1, 2, 3 years, or people just spend all their life since they got permanent position. And this is just data for our distribution. So it's just the same paper. So it's not just exponentially decaying distribution.
Does the VAT top?
Yeah. Just U-shaped distribution. It's not our result. This is result, of course, in mathematical literature, in probability theory. But now we managed to get that result out of our assumption involving residence time dependent escape rate from particular problem. So, what time? Because I could talk another hour. It's,
10 minutes.
10 minutes. Well, this is just advertisement. As long as we have now a mathematical tool to deal with this kind of process, we started to extend to everything, like many nonlinear effects. This is very famous warm sensing phenomenon. That's what I mentioned to you a while ago. Then the biophysical process for microorganisms like cells, bacteria, very much depends on the local population density. Sometimes it's negative dependence, sometimes positive dependence. Cellular adhesion, which involves interaction of neighborhood. Like imagine we have two particles, and the particles want to jump on the right. But since these particles say, no, don't jump on the right, you see, they just, this is adhesion. The same working for, again, for our political system. You see all this information bubble. If you all friends think in one way, believe me, you will not be able to move differently. Because it's social life, you know, if you started to think differently, you will lose your friends, you know. It's so obvious, and then this is kind of behavior of interaction. And if the particle move in one direction, like friends, they move in one direction, no change. So that's typical. Polyphilic effect, which describes cell motility of available space in crowded environment. So, like Brownian particle, they can jump on the right, on the left with the same probability. Just imagine on the right you have a lot of particles. Clearly, the probability of jumping from the right will, if it's socially good place, then it increased probability. If it's not good, too overcrowded. And also regarding anómalo segregation. In the past, like 2 years ago, I used Mexico City as an example of anómalo segregation. You know why? Because it's, just imagine, rural area and Mexico City. Common belief was, it's like Poisson process, just exchange. No, if the person moved from rural area to big city, most likely it will be trapped in big city. At the beginning, it will very uncomfortable situation because, you know, life in outside city is really good, but in city it's not. But as long as you get a job in the big city, friends, all this social network part of the bank, you will behave that way. So that's why we have a lot of agglomeration. Big cities like Moscow, I'm Russian actually. Moscow is just overcrowded. Big cities, São Paulo, London. As long as you, and it's not Markovian process anymore, it involves this kind of behavior. So it's pretty universal. And the same, we publish this result in journals, Theoretical Biology. Subdifusion resolve these nonlinear functions. Well, this is just, of course, if you apply theory for one equation, then you can extend for several equations, and it's also that's what we do. It's a two-state system. It's always two-switch factor. Let me finish. So, thank you very much. And it's also very good, and just another example, like Steve, we published 3 papers in physical review very quickly. He was a PhD student, and then I told him, okay, this now is a nice chance for you to make academic career. But he's from Manchester, and his girlfriend said to him, well, let's chase him for money in London, and then we moved to London. And it's good for him because he was quickly found a job in London as an investment banker. Because nowadays in banking service, they look not about your education. Who cares about your education? They care about your brain. And the proof that you have a brain, good publications, a good journal in theoretical physics and mathematics. So that's the best proof. Just an example. Peter has a career, good career. But again, sometimes you are trapped. Like Nikolai Korabel, he's from grain, and he don't want to move from physics to all these social phenomena I just explained to you. Because he was like, no, I'm just going to do physics. He sticks for physics. No jobs for theoretical physicists. So he just trapped in postdoc position. And already almost 40.
Some question for the Federal?
I have a question and some comments. I would like to start with the comments.
Right. Okay.
Usually in physics, at the very beginning we start the basic physical laws. For instance, when you
start with
the basic physical laws. For instance, just let me just to go to the argument. For instance, if we want to describe Brownian motion, we are not going to be able to describe with the standard second law, Newton's second law, because simply this characteristic of the stochastic that is due to the particles that is surrounding the particle, the Brownian particle.
White noise.
So Langevin in the beginning, just to students, I know that you know, modify the second law just adding a stochastic force. Basically, the information of this stochastic force is the way how the particle has this Brownian motion. Okay. Now there is a very well established way to get from the Langevin equation, which is basically the Newton second law, but with this stochastic noise, and get, for instance, an Fokker-Planck equation. This is a very standard technique. Okay, and then, for instance, for the Brownian motion, you will get basically the diffusion equation that you put in the beginning. Now, in a situation more complicated, for instance, you have more particles. You can also you can write down the many particle Langevin equation, and also with the stochastic forces, and then you can go also to this mathematical procedure and then get the analogous Fokker-Planck equation for the many particle situation and with interactions between them. And then you can go, for instance, to the overdamping limit, and you will get basically
because the closure problem is just one problem.
I mean, you will get basically what we call, I don't know if everybody called in that way, the Smoluchowski equation, which is the equation that describes the distribution of the many particles. I mean, the question is, what is the probability density function for the n particles, for the positions of the n particles, in a certain time when they start, for instance, in zero time. Okay, that's the equation that includes also the interaction between them. Well, you can write down in that equation in several dimensions and also in pure manifolds and whatever you want, basically. Now, when you put, for instance, in one dimension, and you put the interaction between them, you are able to get what is so-called now the single file diffusion, which is a particular single file diffusion, which is a particular subdiffusion process. Basically, the mean square displacement is proportional to t to the 1/2. I mean, the mu is 1/2. And then, I mean, that's a way how to explain from the very physical principles what's happening with this subdiffusion. And as you mentioned, subdiffusion was observed clearly by biologists since 1950, when they studied, for instance, ions crossing cellular channels and zeolites, moving of particles to zeolites, and all this stuff. But my comment basically is that you are, with the basic physical principles, you are able to explain the subdiffusion. So, what you present us, in my opinion, is a very nice tools to describe the phenomena, and I don't have any doubt that this is connected with this other way to derive also subdiffusion. So my question then is, well, there are two questions. The first one is there a way to have this connection? I mean, I don't know, modify, I mean, to develop these fractional derivatives and try to put together with the equation in the standard way, because I know that in the biological systems, I mean, you have many particle interactions, and I mean, it's basically the case, and also you have confinement. I mean, you have these obstacles that provide basically the subdiffusion, which is basically the ingredient why the single file diffusion works. So that's the main question, and the second question is if you are able to write down a Langevin type of equation that basically produce this transport equation that include the Riemann-Liouville partial differential equation.
Right. Okay. There's two questions. Generally speaking, in this anomalous business, generally speaking, and to take into account the interaction between particles, it's never done up to like 2004. It's because it's not easy from technical point of view. It's just technically, as long as you see fractional business involving fractional partial differential equation, you see mathematical literature or physical literature, famous people like Lafter, Ralph Metzler, they're always linear equations, no interaction of particles. So they always consider either one particle, they move, or they consider many particles, but there is no interaction. That's why it's just equivalent description of the same equation. So people only recently started to take into account this interaction of particles. So it's a new area. That's what I'm saying. So that's why the whole program, starting from many particle system, reduction of description, is not done yet. That's a issue. Regarding Langevin equation. Yes, of course, the approach is available, and now instead of, I'll give you an example. Of course, well familiar with second law of Newton, we just write down m d prime, and then now this is standard fiction. Now, in order to introduce anomalous effect, you can say, oh, this doesn't work, and now completely artificially, out of blue, well, it's not local. Instead of linear dependence, you introduce integral from 0 to t with some kernel t minus tau, d tau, and we call, oh, now we have so-called viscoelastic effect. And then, regarding the noise on the right-hand side, we introduce randomness. that it will be not standard white noise because of, again, filtration dissipation theory. This noise also we have long correlation, and then you can get all this subdiffusion effect. That's another approach to deal with subdiffusion. That's right. But personally, although I am a theoretical physicist, I like who doesn't. But if I ask people how to get that kernel, nobody knows. People simply say, "Do you know?"
I think I saw a talk from this people that is working on the extraction of oil from the.
Oh yes, they introduce some modeling,
Yes,
assumption.
they introduce
Yeah,
some-
of course, and this is like phenomenological approach.
Yes.
Of course, people are clever. They've got some ideas how to introduce this memory kernel. Yes, it's the same story for continuous time random walk I just described today. If the physics is not happy with this law, power law, how to get it, then of course it's a lot of microscopic model. You introduce many potential barrier, and then you introduce a particle drop, but then of course you have a standard escape rate, Arrhenius law. You don't need to prove Arrhenius law. But the height is random. Sometimes height is small, sometimes it's large. Then you introduce multiple dropping, again, some assumptions, and then you will get this power law. So again, it's like in physics. But as long as you introduce, I like this law. This is really universal. You can apply for anything. But if you are involved potential barrier to overcome, then you are stick to particular problems. So, but it's done actually. Many works. Oh, this is partially already done.
No, no,